Okay, we start our webinar, and first I would like to say some words about our program of webinars. This is the first one, the first attempt, let's say, and we plan, of course, in the future, in the near future, to organize many other webinars concerning different parts of Topos, different possibilities of our program package. I hope you will join us in the next webinars. Also, these webinars, the next webinars, I mean, will be rather specialized. They will be devoted to some, let's say, special parts of Topos. If you, for example, are interested in some special classes of compounds, special methods of analysis of crystal structures, you can ask us and propose some topics for discussion. For example, if you see in the public chat, Bharat Kumar asked about some special kinds of simplification of crystal structures, and of course it will be one of our future webinars devoted to this topic, of course, because simplification is very important for analysis of the structures. So just propose your topics, and we will of course propose our topics and publish the announcements about new webinars on our website, and we will send you the messages about them. First, let me introduce myself. My name is Vladislav Bulatov, and I'm the director of the Samara Center for Theoretical Materials Science. And now our first webinar is devoted to a special new services, online services that allow you to analyze your crystal structures and to get the topological types for your networks. Let's start with the general task. Let's imagine that you have some crystal structure, and what to do with this structure to determine the topological type. First, I run Topos. I will show you now my desktop. Just a moment. So you see the desktop, and also you can ask questions using the tabs in the same part of your interface during the demonstration. So we have here the Topos database with 3 examples, 3 crystal structures. And the first one is just a very simple coordination polymer with one coordination center. I first compute the adjacency matrix. This is the first step. I compute adjacency matrix using AutoCN. I can use program path. Okay, AutoCN. I use standard options here, default options. This means that I use the default method domains. Please pay attention, because in the recent versions of Topos we have changed the method. Now we have the method domains, a special method that is described in detail in Topos manual, in the last version of Topos manual. Okay, run AutoCN with default option. We get these results, these adjacency metrics. And now I can look at this structure using Isaac-List. Grow a bit. And you see this crystal structure, the cobalt centers, 6 coordinated, octahedral, no clusters here, no polynuclear coordination units. So we just consider this structure in a standard way as cobalt centers plus organic ligands. I run ADS, the ADS program, with the special simplification mode, save simplified net in the ADS options. I think you know, if you worked with Topos, you know this method, but anyway, I repeat them again because it's better to show the whole way to analyze the structure. I use this simplification mode, standard simplification method. Okay. Here I don't need to change anything in the topology tab. Just OK. Run. I create new database with suffix C that contains will contain really the simplified structure. I specify user code Unity. Okay. And here I select metal atoms as centers of the coordination polymer. It's better to use the element tab, the element button, and here metal button, this one. In this case, I will be sure that I have selected all metals in my list. Okay. I get immediately this database, this new database with a simplified structure. Look at it. And I see that we have here some cobalt atoms and some pseudo metal atoms, scandium, titanium, and vanadium. In the comment tab, we can see that scandium really is the center of mass of water molecule. Titanium also water molecule, but disordered, because here we see some extra hydrogens. And the vanadium is the organic ligand. Now I perform the next step of the simplification procedure: compound, auto-determine, simplify adjacency matrix. Okay, I have to remove all 0 coordinated, 1 coordinated, and 2 coordinated nodes from this network to make it in some standard view. 0 coordinated means some isolated molecules. 1 coordinated means terminal ligands, and 2 coordinated are bridge ligands. We transform 2 coordinated ligands into edges of the network. Okay. And now we have this last version of the network, of the underlying net. It's 3-4 coordinated, as you see. And now we have to determine this the topology of this network. So first, let's use standard Topos parameters and standard Topos methods to determine the topology. I again use ADS options, topology, and classification mode. So you know that ADS has 2 main modes. The first one is simplification, and the second one is classification. After simplification, we should use the classification mode in most cases. Okay. we switch between these two modes, and now we use classification mode. Okay, run. I download the TTD collection, but this TTD collection, this version of the TTD collection is not complete. It's free one, because you know now Topos uses two types of the TTD collection. One of this collection is free of charge, and the second one is paid. Really. So now we use standard collection that you have, I think, on your computers. I download it. I have now to select all atoms in the list because I analyze the whole network. I determine the topology of the whole network, or the network of metal centers and ligands. Okay. And we see that we have here new topology. According to this version of the TTD collection, this topology is new. Strictly speaking, to get the whole information, you have to use the whole TTD collection, but this TTD collection is not free of charge. You have to pay for the collection. This is one way. And the second way that is possible now, you can use the online version of the whole collection that is free of charge. And now our webinar, the main purpose of our webinar is to get you acquainted with this part of our services. So we get the information that this topology is new, but we should check if it's really new using the whole version of the TTD. No, okay, I close this window. Now, the best way now is that you need to select this record in the database. Anyway, if you even have just one record, it's better to select it. I will explain a bit later why we need to do this. Select, for example, select all. Select all. Then we again open ADS, and in the options, we use this option, data on new nets. Data on new nets. When you click this option, the Topos will check some other options that are needed to output the information about this new topology. So just answer yes. And now the point is that with this option we can determine the so-called topological indices for this network and save them into a special file called NMT file, NMT, new net topology file. It's a textual file. We will see it later how it looks. And with this file, we can then determine the topology using our services, online services. To compute these topological indices, we need to specify some options in topology tab. First, we compute so-called point symbols, coordination sequences, and so-called vertex symbols that contain information about rings. Here we specify the size, the maximal size of the ring, 10, but we don't know before the calculation what rings are the largest in our structure. So to be sure that we compute all rings, we need to use this option on continuous tab, standard ring limits. In this case, Topos will choose the limit for calculation of vertex symbols itself using some special procedure. and you should not care about correct choosing of this limit. But for this purpose, you have to be in so-called continuous mode. And to be in continuous mode, you have to select the compounds, the records in the database. This is the reason why we need to have selected structures. Even if you have just one structure, select it to pass to the continuous mode. And in this case, all parameters will be standard, and you will be sure that you can compute your topology with some standard set of topological parameters. Okay, now run. We get again the information about this topology that it is new, but now we also have information in the NNT file about topological indices. And let's look to the topological type, to these topological indices. I open the Explorer, and I should find where is this file. By default, this file is in the among the Topos files, the Topos output files. And again, by default, Topos is installed into your C part of the hard disk. I have Russian version of Windows, but anyway, you have to have the same structure of the information. So C part, then users part, then public part, and public documents. And then again, C users public documents. You have Topos Pro, this Topos Pro folder. Here I created a special folder called service example. And in this service example, I can see the last created file, this one, with the name of the database and with the extension NNT. Okay. Again, if you cannot find the file, this folder, you can also use this possibility in Topos. I switch for a moment to Topos again. In Topos, in the system item, Topos parameters, paths. Look at paths. And here in the first line, you have the total path to the Topos Pro files. So you can look which path you need here. This first segment C, users, public documents, Topos Pro. And go again to this folder. I open this NNT file with any text editor, for example, with Notepad. And we see here the information. This is the proposed name for this topology because at the moment Topos thinks that this topology is new. So Topos proposed some name for this topology. But probably this topology again is already known, but it is contained in the database in the whole TPD collection. Okay, so you don't think that this is the real topology name, because first we need to be sure that this is really new. If it is new, really new, you should address to us and ask to input this topology into TPD collection. This is another story, and in the Topos manual there is a special appendix where it is described how to use, how to apply for the name for the new topology. But now let's use this file to check if the topology is really new. Now I need our service so-called SCTMS service client. If you have not downloaded it yet, you can do it using our downloads part of the topospro.com website. This is free of charge, so just download and install it. Now I run it. Okay. How to work with this client? At the moment, the interface is very simple, very easy to use. But with time, we strongly hope that it will be strongly extended, and we will add in the near future new services to this client. At the moment, the first step you should use is to connect to database. File connect. Here you use some special standard IP address and port. Don't change this information. And you should specify here account and password token. For account, you use guest name. For token, you use test. 4 letters, test. This information is provided in our manual, Topos service client manual, guest and test. Okay. And now we have connected to the database. Connected, and now we can use services. We have at the moment 3 services here that provide you with connection to the TTD collection, TTO collection, and TTR collection. I describe in short this collection. TTD collection, Topos topological databases, contains information about topological types. Just topological indices of these types. And now we will use this collection to determine the topology of our network. The second collection, TTO, topological types observed, contains information about the structures where these topological types occur. So this is a list of ref codes of the crystal structures, real crystal structures, where this topology was found before. And the TTR collection, topological types relations, contains information about relations between topological types, how these topological types can be transformed into each other, if it's possible, and if again it occurs in some real crystal structures. I will explain it more later, a bit later. Now let's use the first service, this one, TTD. And here we have 2 modes. The first one, search mode, allows you to find the topology using the name of the topological type. Just type the name, the symbol of the topological type, and you will get all topological types that contain this set of letters, let's say. But in practice, in most cases, you will need this second mode, compare. And this is exactly the mode that requires the NNT file. Now, the next step, we should download the NNT file. Using File, Open. And again, here we need to find the NNT file on the hard disk. we should use here again the standard for topos, standard path, C users, public documents, Topos Pro, and our special folder service example. And here we have this MMT file. Open. We get this information here now. And now just use tools compare. By the way, before running the service, I would like also to show you these additional options here. This is comparison options. These are 4 types of topological indices. This is point symbol, coordination sequence, extended point symbol, and vertex symbol. By default, all of them are used to compare your topology with other topologies. And by default and in general, you need to use all of them, of course. But you can uncheck some of them. For example, vertex symbol, let's say. Uncheck. And this means that you will use only 3 topological indices and probably will find some additional topologies that have the same first 3 types of topological indices, but probably different as the 4th one. This is also the method to find not exactly the topology that corresponds to your structure, but some other topologies that are close to this topology. Very close, have many other topological indices the same, but differ by some special topological indices. This is for experienced users, of course, and in general, again, as I said, you need to use all of them. These additional options limit the number of topologies you get in the output. By default, all these options are specified to 10. This means that, for example, if you get more than 10 topologies, as a result, you will get just first 10 hits. This is a limit that really specified for this free version of the Topos client. We plan to remove this limit for the registered users who paid for our databases. But for other users, these limits will remain in the future. But again, in most cases, this is quite enough. We will see now the examples. So let's first use the default options. And now just go to Tools, Compare. And we get immediately that this is known topology. It exists in the TTD collection, in the complete version of the TTD collection. And the name of this topology is 34L13. What does it mean? You can see the description, the detailed description of all topological nomenclatures in the Topos manual, in the Topos Pro manual. There is a special appendix that is devoted to such kind of description. And this nomenclature is used in Topos. This is Topos nomenclature. This means that we have two kinds of nodes in the structure, 3-coordinated and 4-coordinated nodes. And we saw it before. That's true. L means that this is a layered topology. This is 2-dimensional topology. 2-dimensional. And the number 13 means that this is the 13th topology among these kind of topologies with 2 nodes of this coordination and layered topologies. Again, the first part of this symbol, in general, does not determine it strictly. So there can be different, topologically different, 3-4 coordinated layered topologies. And this is the 13th one among this list. Okay. Now, next step. So at the moment we have the information about the topological type. We can use this information in the paper, for example, to unambiguously describe this topological type, to designate it. Next step. I want to know in which other structures this topology occurred before. Which structures have the same underlying net. And I can do it by a right click here, a right click, retrieve occurrences. Retrieve occurrences, and you see here that there are more than 600 examples with this topology. And to look at them, I can click here, show ref codes, and I get first 10 examples. Let's look for a moment at this table. What does it mean? The first column is the current topology. The second one is a reference code in some database. In this case, this is the ref code from the Cambridge Structural Database. And to get the whole information about this structure, of course, you have to have the Cambridge Structural Database installed in your system, the official version. Unfortunately, we cannot provide the users with the C files with crystallographic information because of copyright limitations, and you need to address to the Cambridge Structural Database for this information. And this Z column contains a number of these units in the same structure. This means that in this structure, for example, we have one independent layer of this topology. If there will be more than one layer, we will have more numbers here. And the last column is the type of representation of the structure. I can spread a bit this column. So you see that, for example, for this structure, we have valence-bounded MOF standard representation. What does it mean? This means that this topology occurs in some metal organic framework or in general in coordination polymer that is valence-bounded, and this is standard representation of this polymer. This means again, what is standard representation for coordination polymers? This means that the nodes correspond to metal centers, and ligands. No clusters, no polynuclear coordination groups here, just metal centers and ligands. And for example, the second example, here we have age-bounded molecular structure, again standard representation. This means that this topology occurs in the structure in the molecular crystal where molecules, organic molecules, are connected by hydrogen bond. So quite different compounds, but with the same topology. In my case, this is a coordination polymer, and of course I will be more interested in, for example, in this structure or this one, also valence bonded MOF, to compare my compound with these compounds. We got just 10 examples, but we can get more examples if we increase this limit up to 100. Again, retrieve occurrences and show ref codes. And now we get the first 100 examples here. For example, by the way, you see the example where in the structure we have two different kinds of the same layer, of the layer with the same topology. but two independent, crystallographically independent layers. You can ask, of course, what to do if you want to get all 663 examples. For this purpose, the answer is please buy our topological collections. But if you want just to give some examples in the paper, you can write that there are totally 663 examples, and there are some examples like this, and you can give some examples in the paper also from this list. And this information should be enough in most cases. Okay. Now, the next possibility here is to retrieve relations for this topology. We can look at other topologies which are related to this one according to some topological transformation. Again, right-click and retrieve relations. And now we really address to the TTR collection, to this collection, topological types relations. While before, we addressed to TTO collection when we looked for real examples of this topology. And here we see that there are really 41 examples of relations of this topology with other topologies. What does it mean? For example, the first column here corresponds to so-called standard representation of the structure, where we have, in the case of coordination polymers, metal atoms and ligands as nodes. The cluster representation means that we have here some clusters, some polynuclear complex groups, dimers, trimers, etc., etc. And for example, these relations, this relation, for example, number 29, means that this topology in the standard representation, so this is our representation, we use really at the moment standard simplification for my structure. It can be related to HCD topology, honeycomb topology, in the cluster representation. So probably if in my structure there are some clusters, some dimers, for example, we can get the topology, a much simpler topology, HCD topology, and very common topology for the crystal structure. If we consider these dimers, these clusters in general, as new nodes of the network. Instead of atoms, instead of metal atoms, we use the clusters. But in my case, there are no clusters, obviously, so no need to consider cluster representation, and we just know about this possibility. Probably in some other cases, we can find the clusters, and in this case, we can get some of these kinds of topology. There are different, you see, different relations here. This is, of course, a special possibility of this service. I think most users will need just first two services, I mean TTD and TTO service. So this is the main possibilities of the TTD service. We can use TTO itself or TTR services, but here you need to know ref code. For example, if we have here the list of ref codes, and you want to see if there are some other representations for this ref code, Akabach, I can type it here. Type it here, just type Akabach bar and search. And we see that there are no other representations for this structure, so just one. This is very simple. For TTR, we need to specify topology. For example, 3, 4, L, 13. Here we need not to start with mode, but equal, strictly equal to this topology. Otherwise, we will find some other topologies that contain this set of symbols, search, and we get this list. First 10 examples. I can increase here the limit and search again, and we get all 41, the same list of examples as before. Okay, so I showed you the main possibilities of this service. Then we will consider some other examples, but at the moment let's stop for 1 or 2 minutes, and you can ask questions if you want using your interface. I stop showing my я думаю, что может там переключиться. Не, он еще что-то. Ну, что сейчас повторим? Да нет, не знаю. Тут можно быть причин. Мы указывали динамическое мировое. Yes, I'm waiting for questions. You can use the question tab in your interface to ask any questions about the services. Please ask at the moment only the questions about the services, about this topic. And in the end of the webinar, you will be able to ask other questions, of course. And you can use the public chat to exchange by the messages. Yes, let's see. Yes, yes, Bharat Kumar. The references are from CCDC. If you have the references, their reference codes like several letters. Let's say this is from CDS, from Cambridge Structural Database. But in some cases, you will have also examples from other databases. For example, if you see some numbers as the ref code, this is from ICSD, Organic Crystal Structure Database. So we have both ICSD and the Cambridge Structural Database implemented into this system, and we take ref codes from them. Okay, so now we proceed. And I again open my my desktop. The second example. The second example. This is really the third one in the list. This one. This is an example of again coordination polymer, but containing not just metal centers, but some polynuclear complex groups. Again, first step, run AutoCN with standard options. we get the adjacency matrix. I again just show you briefly the structure. And you see here clear dimers, pedal wheel dimers. And we can now consider this structure in two ways. The first way, again, is a standard simplification, when we consider these atoms as centers, as the nodes of the underlying network. And the second way is more correct, let's say, is more useful in this case, is the net of dimers. We can consider both ways, and in the paper you can also write, for example, that this structure has this topology in the standard representation, and that topology in the cluster representation. Different kinds of representations allow us to find the relations between different structures. Let's do the first simplification. Run ADS options, and again I switch to simplification mode. Standard, I use first standard method. No need to specify other options. Standard, okay, run. I select again metal atoms, all metal atoms as the centers. Okay, and I get immediately this second record here. Let's look at the list. We have here copper atoms, oxygen atoms, terminal really with coordination number 1, and pseudo-scandium atoms that are the centers of organic ligands. I simplify this structure more with the simplified adjacency matrix procedure. Remove 0, 1, and 2 coordinated. In my case, I have just 1 coordinated. Oxygens, these are really water molecules. Oxygens are water molecules. Okay, yes. And we get this structure 4, 8 coordinated. This is a standard representation. And let's get immediately the second representation. The so-called cluster representation. I close this database with the simplified structures. I again open our ADS program, options, and I switch the simplification method from standard to cluster. Okay. Again, no need to change other options. Okay, run. And here in the cluster mode, I need to select all atoms, not just metal atoms, but all atoms, because we consider here the whole structure and ask Topos to find clusters in this structure among all atoms, considering all atoms. Okay. We get one example, this one, and just look at the structure for a moment. You see here some dashed bonds appear. These dashed bonds are pseudo-hydrogen bonds in Topos. This means that these are intercluster bonds. And if I uncheck the hydrogen bonds in the options, I will hide them. I grow the structure. You see that it is not, it doesn't grow more. It doesn't grow more. And we have here separated dimers. So Topos found these dimers automatically. And now we can simplify this structure, considering these dimers as structural units. Okay. Now again, run ADS already for this structure where the dimers were separated. Options. Now we switch again to standard method and change this parameter, this type of bonds. We have now valence bonds as interatomic bonds, intercluster bonds, let's say, and hydrogen bonds as valence bonds as intracluster, internal bonds. H bonds as intercluster, between the clusters, or intermolecular, it is called in Topos. So we need to specify them in this way. This means that I consider this structure as a set of structural units with valence bonds connected within themselves with valence bonds and connected with each other by hydrogen bonds. Okay, run. I create the next level of the simplified databases, CC. Yes, code one. Okay, and now we use whole molecule mode because we have no central atoms here. We have clusters as the structural units, the molecules, let's say, and we get this simplification. Here we have pseudo metal atoms again. The chromium atoms, pseudo chromium atoms, correspond to dimers, copper 2 dimers, to the pedal wheel dimers. And other atoms correspond to parts of organic ligands. Now we simplify it more again. Simplify adjacent symmetrics. Okay. Okay. Again, we have 3, 4 coordinated net, as in the first example, you remember. But if this the same topology or not, we don't know, and we should determine it. Let's do it one by one. First, I consider this database with the first simplified variant. Here we have again, I remind you, the structure simplified in the standard way. ADS, options, topology classification. I try to classify. I don't need H bones here. Just classification mode, standard classification mode. Run. Download TTD collection. Yes. And sorry. We have to use not this one, but this one. This is the first simplified structure. Again, run. Yes, 8 coordinated network. I select all atoms. Okay, and I get new topology. I specify data on new nets now to create the NNT file. Okay. I close this window for a moment to select this record. I need to have it selected, and for this purpose you can use, for example, insert button on your keyboard. Now run again. Options, yes. Data on new nets. Run. I overwrite this file, NNT, the old one. I don't need the old information. By the way, you have to have in the NNT file just one topology to use the Topos online services. Because if you have several topologies, it is possible, of course, but the service will take only the first one for the analysis. So create, for this purpose, different MMT files with one topology image. Yes, we did it. And the topology is new. Okay. Now let's go to the second simplification here with 3-4 topology. And I do the same. Select all, for example, select first. Then run ADS with the same options. And this topology is new also. But now we will use our services to determine if they are if these topologies are really new. So I have already the client downloaded. I switch to the TTD service, to this one. Again, I download the first file, this one. You see, this is 4-8 topology. By the way, the letter T means this is three-dimensional topology. This is three-periodic one. And tools compare. And we get again some kind of known topology. This is again a special nomenclature, Topos nomenclature. The detailed explanation of this nomenclature can be found in the Topos manual, in a special appendix, as I said before. And you see that this is a net with collisions. It has collisions, so-called collisions. And of course, it's not surprising because these dimers, if we consider them separately, I mean the atoms inside dimers separately, the dimers provide collisions in the network, in the resulting network. I will not look at the other examples of this topology. We will do it for the next one. But we just know that this is again the known topology and with collisions. Now I open the second file, this one, with this 3-4 topology. And you see, by the way, that this is not layered topology as in the previous example. This is three-dimensional topology. So this is another topology, let's say. Tools, compare. And we get again known topology. So you see here two names of this topology. The first three-letter name is from the RCSR database, from the database by Michael Keith. And the second alternative name is the Topos name again. Right-click, retrieve occurrences, and we get totally 65 occurrences. Show records. And we have here all of them, because this number is smaller than 100. We have all examples. And by the way, you see here that there are examples of the single networks. For example, the first three examples. But these examples really contain, these structures contain 4 different frameworks, 4 interpenetrated frameworks of this type. Here you see 3 interpenetrated frameworks, etc., etc., 2 interpenetrated. So you have the whole information about this topology in different structures with different kinds of catenation also. Okay. All of them, by the way, all of them are valence bounded. Let's look at this last column. Standard cluster representation. This means that here we used standard method for cluster representation as we did it before. And I bet that almost all of them, many of them at least, contain dimers as our structure. But there are also, you see, the structures where this is not the cluster representation, this is just standard representation, and probably these structures are different, are organized differently compared to our structure. Okay, I can also, of course, look at the relations between this topology and other topologies, but I would not like to concentrate on this part. So this is again rather special part. So I interrupt here again for a moment, and you can ask questions if you want. And if there are no questions, other questions, I proceed with the last example. With the last example. The last example, this example is the example of organic structure. Let's first compute the adjacency matrix. So you see here there are hydrogen bonds between molecules. And now let's look again at the structure. I show hydrogen bonds here, you see. These are some molecules connected to each other by hydrogen bonds, and again you can easily see here some double layers of the molecules, double layers connected by these bonds. Let's determine the topology. Let's simplify the structure first. Switch to safe simplified net mode. We use standard method for molecules, for molecular structures. This means that I consider molecules, valence bonds between the atoms, and H bonds, hydrogen bonds, as intermolecular bonds. Whole molecule. And we have this structure with just one node, and this node corresponds to the molecule. Okay. Now I select using insert button, insert key, this record, and immediately run ADS in the classification mode and with the data on units mode. Okay, run. I overwrite the old NMT file. I get again the new topology, and now I go to the client, open the file, this one. So this is 5L1, but this is just some proposed name for the new topology again. Compare, and I get this topological type. This is sphere packing, two periodic sphere packing, a special kind of topologies that were generated by Fisher and Koch You can find again the reference to the work of Fisher and Koch in the Topos manual. This is rather typical layered topology, well known, and let's be sure that this topology is very well known. Retrieve occurrences. Almost 300 examples of this topology is unknown really. Show these web codes, and we get the first 100 examples. Here, by the way, in the top, you see some examples from inorganic structures. These are ref codes from inorganic crystal structure database. And this is complete representation. This means that these structures are completely considered without simplification. And this is not again surprising, because you see from the name of this topology that one of the names of this topology is tin sulfide. So it really occurs in inorganic structure. But there are also valence-bonded MOFs here, and also H-bonded molecular structures. And probably these structures with this representation, H-bonded molecular structures, are very close to my structure in some way. So this is the method to find the relations between the topologies of different structures, chemically different, but topologically similar. Okay, that's all for the examples, and I interrupt showing my service. Yeah. Okay, if you have questions at the moment, please ask them. And we will have the webinar, similar webinar on Monday, next Monday, but in the evening by our time, let's say. And importantly, the video record of this webinar will be available very soon. And you can also say to your colleagues to look at the webinar offline, let's say, if they are interested in this topic. And also you can ask us other questions if you have them by email. And I hope to see you in our next webinars. Okay, now we stop. And if somebody wants to say any words, we can. Okay, I see some questions. Okay. Yes, David, we will talk. We can talk immediately after the webinar. So don't stop your session. Okay. So I say goodbye to. Sorry. Okay, Christoph. Okay, thank you also. Also for using Topos, very active using Topos. Thanks to everybody, and please use these services and ask us more questions. If you want to know more about them. We will announce other webinars, I think, very soon. So just join us again. Thanks. Так, а ты можешь их отключить отдельно?